All right, so this is an interesting question. The question is, if I wanted to figure out what is the height of this, so let's say that I wanted to do like an exact height, like a pretty straight line right there. Or let's say I wanted to do like a perfect diagonal here. Could I calculate that? Well, yeah, you could, because in fact this does, like a right angle kind of thing. And this has right angles here. So we got some right triangles, which means we can do some Pythagorean theorem. And that is just cool. Who doesn't like that? I do. I love it. So let's see if we can take apart these. Let's do them one at a time. So first, I'm looking at this one. And, let's see what's smaller there. So I want to look at this piece, and I see that all three sides are 4. But this side here, I'm splitting it in half. Perfectly in half. It's like I bisect this angle there, and then these angles. So these are the same, and then these are the same here, and that's going to bisect these perfectly in half. So I'm going to cut that in half, and that puts this side at 2 and this side at 2, and then I'm right in the middle. How do I know that? Well, this is an equilateral triangle, and equilateral triangles can be split down the middle with a perpendicular bisector. It also becomes an angle bisector. It's got all this great symmetry. So I have a 2 and a 4, and let's say like this is my height. We'll call it h here. So there's my height. Now if I wanted to figure out how tall that was, I would do, good old Pythagorean relationship. We got 2 squared, and then an h squared. And then what do we have here? A 4? That would be a 4 squared. All right, now taking it a little bit further, this would simplify to a 4. This would become a 16. We'd have the plus h squared there, and then I'd get h squared equals 12 when I subtract 4 from each side. Then I'd say, well, then h is the square root of 12. So that's awesome. Perfect. Well, but you actually see a little bit more of a pattern when you kind of simplify this. And 12 would actually be 4 and 3 if I factored it out. And the reason I would factor out the 4, not like a 6 and 2, because the 4 is a square. So the square root of a square is just itself. So what's the square root of 4? That's 2. And that's 3 still. So we got h equals 2 times root 3. So I start to see a pattern here. I got a 2 here. This is a multiple of 2. It's 2 times square root of 3. And 4 is also a multiple of 2. It's 2 times 2. So the question is, does that pattern kind of hold true for like everything? Well, yeah, it does. And I'll prove it to you. Let's call this x. And we'll call this h there. And this would be, well, that's double that. And we know it's double it because this was half of it. So that would be 2x. So we need to figure out what would the h be. Well, we know that x squared plus h squared equals 2x, the whole thing squared. That's important because it's not just 2 times x squared. It's 2x, the whole quantity, squared. So the x squared still stays the same. The h squared still stays the same. On this other side, we'll have 4x squared. Now we can regroup these x squareds here. So if I subtract x squared from both sides, and I'm kind of moving it over to the other side, then h squared becomes 3x squared. And then I could, square root and stuff. H is going to be, all right, now what's going on here? Let's pull the number out of the variable here. That would give me square root of 3 and square root of x squared. Well, square root of x squared, that's like an easy square. That's just x. So I got square root of 3 times x. What is this really doing for me? That's just saying that x equals, or pardon me, not x equals, no, not that. H equals x times the square root of 3. So if this were x, then this is double, and this is x square root of 3. That's cool. So 2 root 3, 2 times 2, x root 3, and 2 times x. Cool pattern there. So let's use that pattern. here's an example of how we could use it. Like let's say I wanted to look at number 22 here. Zoom in on it for us. So if I'm looking at number 22, this is actually, that's 30 degrees, that's 90 right there. And we could say, well, then this is 60 because it's got to add up to 180. But this is half of that triangle, that equilateral triangle that we saw. So if I'm kind of drawing an extension here, making this into an equilateral triangle, then that means all three of the sides are the same length as this full side here. So this would be 4 root 3. And this whole thing here would be 4 root 3. But then I got to split that up into 2 halves. Well, this half here would be 2 root 3. And this half would be 2 root 3 because it's, half of 4. So then 2 root 3 plus another 2 root 3 makes a total of 4 root 3. So that's cool. I know that y equals 2 root 3. But then the question is, well, what's x equal? Well, let's just do a Pythagorean theorem. We got 2 root 3 there. So that's 2 root 3 plus x squared. So square that. Then we're going to add x squared in there. So, like leg squared plus leg squared equals a hypotenuse squared. 4 square root 3 squared. And what does this do for me now? All right, so square this. That's 2 times 2 and square root of 3 squared. So it's really 4, and then that becomes a 3. So 4 times 3 for that term there. Then we got the x squared. Now similarly over here, that's 4 root 3 times 4 root 3. So it's going to be 4 times 4 is, well, that's 16. And square root of 3 times square root of 3, that's 3. So then I got 12 plus x squared equals, well, it's 16 times 3. That's 48. All right, now let's keep going. So if I subtract 12 from both sides, then I got x squared equals 36. So x must equal 6. Cool, so I got y equals 2 root 3 and x equals 6. Now if I really, really wanted to check this, I could plug it back in and see what comes out of it. Well, let's look at another one that's, a lot like that. So now, how about I zoom into this one here? It's very similar, very, very similar. So again, we got this thing where we have like half of an equilateral triangle. So if I just kind of extend this like that, and I'm kind of going off the screen. Let's zoom up even more. So I extend that up there, extend this way. Cool, there we go. And then we'd have a lot of stuff happening. So I got x on this side, I got x on this side, because it's just as long as that side. It's like a full side. And then over here, this is x. But here's y. Y is like half of x. So that's like y times 2 equals x. Or x equals 2y. Why would that be helpful? Well, if I did like leg squared plus leg squared equals hypotenuse squared, I could say that y squared plus x squared equals 3. Or whoa. That's wrong. Y squared plus 3 squared equals x squared. But instead of saying x squared, I'm going to say 2y. I'm going to plug that in for x right there. And that would give me y squared plus 3 squared equals 2y quantity squared. Now with this, well then I'll have y squared plus 9 equals 4y squared. I could subtract a y squared from both sides. Then I got 9 equals 3y squared, divide by 3. 3 equals y squared. Then what does y equal? Y equals square root of 3. Alright, so this right here, this piece down here, this is square root of 3. That's cool. Then what's x? Well, x is 2 times y, which is 2 times square root of 3. So this is 2 square root of 3. So pretty cool stuff there. Pretty cool. We're going to go ahead and end the video there. That's a good place to stop, but we're basically looking at this like half an equilateral triangle. The next one we're going to look at half a square. probably even easier.